In this video, we are going to look at a little bit of terminology and notation that you might be familiar with. So we are having, again, two numbers, a and b, integers, and neither of them is 0. Then we call the greatest common divisor of a and b the GCD of a and b. And we call the least common multiple of a and b the LCM of a and b. So greatest common divisors, if you have a number, say 4 and 8, then the GCD of 4 and 8 is 4. It's a divisor of both 4 and 8, and it's the greatest such divisor. And the LCM of 4 and 8 is the least common multiple. In this case, it would be 8. Since both, it's a multiple of 4 and of 8. If the greatest common divisor of two numbers is 1, we say that a and b are relatively prime. Relatively prime. Let's look at a few more examples of the GCD before we look at theorem 0.2 to illustrate what we want to look at. So for part A, what is the GCD of 4 and 9? Well, they don't have anything in common. No no divisor. The divisor of 4 are 1, 2, and 4, and the divisors of 9 are 1, 3, and 9. The greatest common one is just 1. So 4 has divisors 1, 2, and 4. 9 has divisors 1, 3, and 9, and well, they have nothing in common, so the greatest common divisor is just 1. What about 12 and 8? They are the greatest common divisor. Let's write them down. For 12, we have 1, we have 2, we have 3, we have 4, we have 6, and 12. Those are all the divisors of 12. And for 8, we have 1, we have 2, we have 4, we have 8. And there we actually have, both of them have 4 in common. That is the greatest common divisor. So the greatest common divisor of 12 and 8 is 4. Now, what's interesting about the greatest common divisor is that you can always write it as a linear combination of the two numbers. So we can write 1 as a linear combination of 4 and 9. So 4 times something plus 9 times something. Let's see if we can find those numbers to put into the parentheses. And those are not unique, so you could play with this. You can pause the video, play with this a little bit, and then see if you come up with the same solution that I come up with. One is, so if you think about multiples of 4, 8, 12, and so on, you look at multiples of 9. Do you see any combinations that would give you a 1 in there somehow? Well, you can see one of those numbers to put in the parentheses definitely has to be negative, but that's okay. And so one way that would work would be -2 as a multiple of 4. That would give us -8. And then if we add 9, so we just put a 1 in here, this would work. It's not the only way. You could play this game and think 27 and 28. One is a multiple of 4, one is a multiple of 9. Again, there's a difference of 1, so you could use those as well. So that's how we get the GCD of 4 and 9. Let's see how we can write the GCD of 12 and 8. So 12 times something plus 8 times something. And what works here? 12, actually, if I just take 12 and then if I subtract 8, I'm exactly where I want to be. So 12 times 1 plus 8 minus 1 is equal to 4. And we can always do this, and that's what theorem 0.2 says. It says that if you have two numbers a and b, two integers a and b that are not 0, then there exists integers s and t such that the GCD of a and b is equal to a times s plus b times t. So we can write the GCD as an integer linear combination of a and b. So in our example right here, minus 2 and 1, minus 2 was s, minus 1 was t, and in our second example we had s as 1 and t as minus 1. So that is our t right here.